AC and DC performance characteristics of operational amplifiers. So under that, the first one, DC characteristics of operational amplifiers. Now we will see. Generally, an ideal operational amplifier draws no current from the source and its response is also independent of temperature. However, a real operational amplifier, that is practical operational amplifier, does not work this way. Current is taken from the source into the operational amplifier input terminals. Also, the inputs respond differently to current and voltage due to mismatch within the transistors. A real operational amplifier also shifts its operation with respect to temperature variations. These non-ideal DC characteristics that add error components to the DC output voltage. Those are input bias current, input offset current, input offset voltage, and thermal drift. Now we will see one by one. The first one is input offset voltage. So this is one of the DC parameter of input offset voltage. It is defined as the voltage that must be applied between the two input terminals of an operational amplifier to null or zero the output voltage, that is a 0, in order to make output voltage to 0 volts. The circuit diagram shows two DC voltages are applied, VDC1 and VDC2. These are applied to input terminals, VDC1 at non-inverting terminal and VDC2 at inverting terminal, to make the output voltage to 0 volts. So here VIO is the difference of two input DC voltages, VDC1 minus VDC2. Here VDC1 and VDC2 are DC voltages which are applied at input terminals of operational amplifier, and RS represents the source resistance. VIO is the difference of VDC1 and VDC2. It may be positive or negative. For example, in 741 IC, the maximum value of VIO is 6 millivolts. It means a voltage plus or minus 6 millivolts is required to one of the input to reduce the output offset voltage to 0. The smaller the input offset voltage, then the better the differential amplifier, because its transistors are more closely matched. Next, the second DC parameter is input offset current. The input offset current, say the difference between the currents into inverting and non-inverting terminals of a balanced. Here, the input offset current is nothing but the difference of two input currents, that is the amount of currents which are present at input terminals of operational amplifier, that's IB1 minus IB2. The IIO for the 741 IC is 200 nanoamperes. As the matching between two input terminals is improved, the difference between IB1 and IB2 becomes smaller. That is, the input offset current value decreases further. For 741 IC, the input offset current is 6 nanoamperes, minimum value. Next, the third DC parameter, input bias current. The input bias current, that is IB, is the average of the current entering at the input terminals of a balanced operational amplifier. That is, the input bias current IB equal to IB1 plus IB2 divided by 2. For 741 IC, the input bias current is 700 nanoamperes. For precision 741 IC, the input bias current is 7 nanoamperes. Next, the fourth DC parameter is thermal drift. Bias current, offset current, and offset voltage change with the temperature. A circuit carefully nulled at 25 degrees centigrade may not remain. So, when the temperature rises to 35 degrees centigrade, this is called drift. Offset current drift is expressed in nanoamperes per degree centigrade. These indicate the change in offset for each degree Celsius change in temperature. Next, AC characteristics of small signal sinusoidal applications. The AC characteristics are frequency response and slew rate. Now come to the first one, frequency response. An ideal operational amplifier has an infinite frequency response and can amplify any frequency signal from DC to the highest AC frequencies. So it is therefore assumed to have an infinite bandwidth. With real operational amplifiers, that is in practical case, the bandwidth is limited by the gain bandwidth product, which is equal to the frequency where the amplifier's gain becomes unity. Open loop frequency response of operational amplifier. So this figure represents the open loop configuration operational amplifier frequency response. So it can show up to 10 hertz the maximum response, and thereafter it goes on decreasing. From this frequency response curve, we can see that the product of the gain against the frequency is constant at any point along the curve. Also that the unity gain frequency also determines the gain of the amplifier at any point along the curve. This constant is generally known as gain bandwidth product or simply GBP. Therefore, the gain bandwidth product equal to gain is multiplied with bandwidth, that is A into bandwidth. For example, from the graph, the gain of the amplifier at 100 kilohertz is given as 20 decibels or 10. Then the gain bandwidth product is calculated as gain bandwidth product equal to open loop gain A into bandwidth, that is 10 into 1 lakh hertz, which is equal to 10 lakhs. Similarly, the operational amplifier gain at 1 kilohertz equal to 60 decibels or 1000. Therefore, the gain bandwidth product is A into bandwidth, that is 1000 is multiplied with 1000 hertz, which is equal to 10,000, 10 lakhs. Next, the second AC characteristics, slew rate. The slew rate is defined as the maximum rate of change of output voltage for unit of time under large signal conditions and is expressed in volts per milliseconds or microseconds. So the slew rate SR equal to the rate of change of output voltage, which is expressed volts per microseconds. To understand this, consider the charging current of a capacitor, which was shown in the figure. See here, the current within the capacitor I equal to C into dV by dt, where dV by dt equal to I divided by C. So there is a curve, time versus output voltage across capacitor. It's a linear wave shape. So with respect to time, what is the change in output voltage? That is nothing but slew rate. So for small amount of time, what's the change within the output voltage? That tells us about slew rate. Slew rate tells us about the rate of change of output voltage. Within this, if I is more, capacitor charges quickly. If I is limited to I maximum, then rate of change is also limited. Slew rate indicates how rapidly the output of an operational amplifier can change in response to changes in the input frequency with input amplitude as constant. The slew rate changes with a change in voltage gain and is normally specified at a unity gain. If the slope requirement is greater than the slew rate, then the distortion occurs. For the 741 IC, the slew rate is very low, that is 0.5 volts per milliseconds, which limits its use in higher frequency applications. Thank you.